I'm Anil Kumar. Welcome to my series on sketching graphs. Let me thank all the viewers and subscribers who think that this is the ultimate channel of learning. And that actually puts a lot of pressure on me to provide you with the best. Now we'll actually learn all the concepts to sketch any logarithmic function. So here we have four related questions. We'll sketch the graph of the following: y equals to log to the base 2 of x. So I've taken base 2 in all the examples. It could be any base. But the very first graph will sketch logarithmic function from the exponential function. As you know, logarithmic function is inverse of exponential function, so it makes sense. And then b, c, d, e are f of x equals to log to the base 2 of 1 over x. Then we have log to the base 2 of 8x, log to the base 2 of x cubed. And finally, we'll summarize all what we have learned in one graph, which will be p of x equals to minus 2 log to the base 2 of x minus 1 plus 3. Okay, so let's begin with y equals to 2 to the power of x as our first graph. So I'm assuming here that most of you know how to sketch exponential function graph. So I'll be rather quick on that. The exponential graph, as you know, looks something like this. 2 to the power of x will look something like this, right? So that's how it is going to be, right? Now, anything to the power of 0 is always 1, correct? Anything to the power of 1 will be the base itself. So this point, which I could write this as 1, 2, and anything to the power of minus 1 is the reciprocal, so minus 1 half, correct? So we get these three very important points. Let me call these points as A, B, and C, okay? Now, whenever you are sketching a graph, you need to actually show 5 key features, right? So basically, remember one thing, sketching means what? If you really need full marks and, if you have to complete the job of sketching a graph, you need 5 key features. Now, in this exponential function, what are your key features? Let's list them out. Try to understand the concept, right? Okay. So 5 key features here are, number 1 is that when x approaches negative infinity, this end, the y approaches 0, right? So that is a horizontal asymptote. So what is horizontal asymptote here? The x-axis, which is y equals to 0, is the horizontal asymptote. So that is also a part of this particular graph, which we are saying 2 to the power of x, right? Many students will miss on this. And if I am your teacher, I'm going to deduct 0.5 marks for that, to be very frank. So that is my feature number 1. Now you get it. Feature number 2 should be what? Well, when x approaches positive infinity, y approaches positive infinity, as you can see from this part, right? That arrow indicates that x value is increasing and y value is also increasing. Both are going towards positive infinity. Now collectively, we call these two features as end behavior. Okay, so that's kind of very important. So end behavior is very important for any graph, especially for exponential and logarithmic functions, correct? So we have listed actually 2 key features. Now we will list 3, 4, and 5 as critical points. So now I'm going to list critical points here, right? So now key is points. So on a graph, for accuracy, we really don't need a graph paper. We need these points, right? So one of the points is that anything to the power of 0 is 1. So one of the critical point is 0, 1. So I'm not writing from left to right this time, But anything to the power of 0, that is 2 to the power of, what I'm trying to say is 1, right? So that is the value. Now, anything to the power of 1 is the base function. So 2 to the power of 1 is 2. But if I write minus 1, then what you get is the reciprocal in this case. So 2 to the power of minus 1 is 1 over 2. So these are the key features for your exponential graph. Perfect. Now, from the exponential graph, we are going to sketch the logarithmic function. How are they related? Well, logarithmic function is inverse of exponential function, right? That is the key, right? Now, inverse means what? Inverse basically means just flip these points. So the points here, which are the key features, become 1, 0, 2, 1, and half minus 1, correct? So those are the points. As far as the behavior and behavior is concerned, when you flip this, what happens? Well, think about it. The horizontal asymptote now becomes the vertical asymptote. Is that clear to you? So the horizontal asymptote becomes the vertical asymptote, right? So on my graph now, we are going to approach not 0 to the negative side when x is very large. However, we are going to now approach infinity, right? So it's kind of inverse, right? Okay. The point which is 0, 1 will now become 1, 0. So this point will come to this point, 1, 0, right? This point, which is minus 1 half, will be now shown at what? Half and minus 1. So at half we get minus 1. That makes sense. And the point which was 1, 2 will now be at 2 and 1. Right? 2 and 1 will be, say, somewhere here. Is it okay? So those are your critical points. Correct? Now, one more thing you remember is that sketching a inverse of a function basically is also a reflection on y equals to x, right? So let me sketch y equals to x here. Okay, so this is my line, y equals to x. So as you can see, these points actually are reflected on this side. So let's say this point was here, so we just reflect this point. So original points are these for me now. Okay, so we just reflected them on this particular line to get the new points. You get the idea, right? So the logarithmic graph could also be sketched as a reflection on the line y equals to x, as I've shown here. So this is your graph of log to the base 2 of x. Is that clear to you? So you have learned actually a couple of methods. In fact, all the methods you may need or learn to sketch logarithmic function from an exponential function. Logarithms are inverse of exponential functions, so they are reflected on the line y equals to x. The key points here are 0, 1. At 0, the exponential function will always result into 1. At minus 1, you get reciprocal, and at 1, you get the same as the base. So those are the three critical points. The end behavior, x approaches to minus infinity or x approaches to positive infinity, gives you the other key features, the end behavior. So as you can see here, when x approaches negative infinity, y approaches 0, that makes x-axis as your horizontal asymptote. Now when we talk about the logarithmic functions, that horizontal asymptote gets reflected on this y equals to x and becomes a vertical asymptote. Perfect. Now from here, let's move on to logarithmic functions, right? So now in logarithmic functions, clearly you can see what is the domain, right? So the domain of a logarithmic function here, we're talking about logarithmic functions, okay? Log to the base 2x. The domain is that x has to be greater than 0, right? And what is the range? Range belongs to real numbers. There is no restriction on the range, however, now the domain is restricted. Does it make sense to you? S inverse of exponential function. I think that's a good introduction to your logarithmic graph. Now onwards, to sketch rest of them, what are we going to do? So all these are basically transformations, correct? Okay, so these are the transformations of that graph log to the base 2x. You could actually sketch any graph, any base using this concept. Now in the next page, we will see how to sketch the graphs for B, C, D, and E. You'll also notice that these are not the very standard ways you see in your textbooks, but these are very standard ways in which you see in your test papers. So that makes my videos especially good for those students who care for understanding and who are trying to achieve the best. So let's move forward and understand now how to sketch the other graphs of logarithmic functions. So I hope the graph of log to the base 2 of x is absolutely clear and you understand how to sketch it from the exponential function 2 to the power of x. So let me summarize. There are 5 key features which you have to keep in mind. 2 of them relate to end behavior and these are your 3 critical points. We are now going to see all these transformations with respect to these 5 key features, right? And we'll sketch the graph of log to the base 2 of 1 over x, 8x, x cubed, and here we'll sum up everything what we have learned so far. Perfect. So let's now take the next graph, which is f of x equals to log to the base 2 of 1 over x. Now, what does that really mean, right? So this is an interesting way of writing the logarithmic function. When we write log to the base 2 of 1 over x, we're trying to say this is log to the base 2 of x to the power of minus 1, correct? So obviously this minus 1, when applying the power rules, can now be written as minus of log to the base 2 of x. Now that tells you what? Well, clearly it tells you that this graph is reflection on x-axis, correct? So it's a vertical reflection. So it is a reflection on the x-axis, correct? So we are always considering the base function, which is y equals to log to the base 2 of x. So with respect to that, this is a reflection, correct? Now let's sketch this function. So here is a quick sketch for the same thing. We had the graph which was kind of like this. Vertical asymptote going up to infinity, right? 3 critical points. This one is 1, 0. Here we have a point which is for log to the base 2, it is half minus 1, correct? And here we have a point which is for 2, the value is 1, right? So whenever the base is same as x value, then what you get is 1. So these are your 3 critical points. End behavior are the key features, correct? Now what are we saying? We are saying we want to sketch log to 1 over x, which is same as minus of log x, correct? That means we are going to reflect it on the x-axis, correct? This is an invariant point that is not going to change. However, this point will change and it will be reflected. So we'll get this point at half 1, correct? This point here will now become what? It will be reflected on this side, correct? So what you get here is at 2, the value will be minus 1. So the y values become negative sign, right? So what you get here is basically a graph which will be kind of like this, right? So this point will be invariant, correct? Do you see that part? So that is how the graph is going to look like. So this point here is called the invariant point, the point which does not change. Perfect. So we started with the graph of log to the base 2 of x. We know the key points here. So if you want, you can actually write down the key points also. That helps, right? So the key points which we had been talking about are, for log to the base 2 of x, we know that if it is half, then the y value was 1 minus 1. If it was 0, at 1 it was 0, and at 2 it was 1. So for 1 of x, this value of y became negative. So we get half 1. At 1 it remained 0, same value. At 2 it became minus 1. The other point here was when x is approaching negative infinity, it is approaching negative infinity. When x is approaching 0 from the positive side, y approaches negative infinity. Correct? When you are going to reflect, that is minus of log 2 of x, this becomes negative, right? So when you're approaching 0 from the right side, the y value is approaching positive infinity. Correct? On this side, when x is approaching positive infinity, then y is also approaching positive infinity. However, the end behavior kind of reverses. So when x approaches positive infinity, y approaches negative infinity, as can be seen here. Correct? So that becomes the graph of log to the base 2 of 1 over x. Is that clear to you? Perfect. Now let's look into the next graph, which is g of x equals to log to the base 2 of 8x. Now what is this function? It may be confusing at times, right? You have to apply logarithmic laws, right? Laws of, or rules, I should write, rules of logarithms. So basically these are rules of logarithms. So when we have log to the base 2 of product, it could be written as log to the base 2 of 8 plus log to the base 2 of x. Now 8 is what? 8 is 2 cube, right? So that means we are saying 3 plus log to the base 2 of x. That means basically we are saying log to the base 2 of x plus 3. Now that plus 3 means it is a vertical translation, right? So it is 3 units up. That is what we need to do. So to sketch the graph this time, what are you going to do? Well, the original graph, log to the base 2 of x, could be sketched something like this, right? This is log to the base 2 of x. 3 critical points, once again, are these, right? These points for us are, so at 1 we have 0, at 2 we have 1, and at half we have minus 1. When I'm saying plus 3, in that case we are adding 3 to the y values, right? So this point moves by 3 units up, right? Let's say this is 3 units up. So this also moves 3 units up. Let's say this is 3 units up, correct? This point also moves 3 units up, correct? So we're kind of going away from the page. So we get these points. So that is a translation, correct? So the graph will be parallel to this, but 3 units up. So let me just sketch the graph here first, right? And the points which we need to show are these points. The value will be 2, 4. Add 3 to y value, right? So here it will be 1 and 3. And this value is going to be half and 2. Does it make sense to you? And it is approaching infinity as x approaches infinity. And when you approach 0 plus, right, this is 0. You have to approach 0 plus to get a value which is negative infinity. Does it make sense? So we have sketched the graph of log to the base 2 of 8x. Is that clear to you? Correct? You can now also write down the coordinates of the points. The original points were 1, 0, 2, 1. This was half and minus 1. So these 3 points, now y value gets added. So you get half and 2. This becomes 1 and 3. and this becomes 2 and 4. Perfect. As far as end behavior is concerned, when x approaches negative infinity, again I write this. When x approaches 0 from the positive side, y approaches negative infinity. In this case, it remains same. When x approaches 0 from the positive side, y approaches negative infinity. Clear? When x approaches positive infinity, y approaches positive infinity. That remains same, correct? By moving up by 3 units, it doesn't make a difference to infinity, right? So those are our points for the transformed function log to the base 2 of x when we transform log to the base 2 of x. Is that clear to you? Perfect. Let's move forward. Now we have the function which is h of x equals to log to the base 2 of x cubed. That means what? So if I'm writing log to the base 2 of x cubed, it really means 3 times log to the base 2 of x, right? So that means what? It really means that now we are doing vertical stretch by a factor of 3. Is that clear to you? So now what happens to our critical points? The original critical points were kind of like this. When x approaches 0 from the positive side, y approaches negative infinity. These are the points which I am now writing for log to the base 2 of x. Correct? And if we had minus half, if we have half here, we get minus 1. For 1, we get 0. And for 2, we get a value of 1. Now, with the transformation, we have log to the base 2 of x cubed, which is same as 3 times log to the base 2 of x. So the y values will get multiplied by 3. Infinitely large values will remain infinitely large. Correct? Does it make sense to you? Correct. So, keeping that in mind, here is my transformed set of 5 critical characteristics and values. So when x approaches 0 from the positive side, y still approaches negative infinity. The point which is at half gets multiplied by 3, so we get minus 3 here. At 1, we still get 0. This is invariant point. At 2, we get 3. And when x approaches infinitely large value, y also approaches infinitely large value. So you see this point is invariant, right? It is same in both the cases. So let me quickly sketch this function also, right? So now I'm not writing the points, but just showing you both the graphs. So if one of them is like this, which is log to the base 2 of x, the vertically stretched graph will be like what? Well, this point still remains the same, right? This point remains the same. That points become more negative, right? This point becomes more positive. So that is kind of a stretch. Do you see that portion? So now the graph is like this. So that is your vertically stretched graph for log to the base 2 of x cubed. Perfect. Now, as an added exercise, you can always add domain and range to your transform functions, right? So that could be an added exercise for you. I hope that makes sense, correct? So let's move on and take the next example. Now this example is combination of everything. So I hope you have understood all the concepts. At this stage, we are going to take a small break. I'll share with you a wonderful thing which I saw in the morning. It was a misty morning. Everything was not very clear. And see what we could see very clearly, close by, just few feet away. That'd be interesting. And after that break, we'll take up the transformation of this logarithmic function. Thank you. So I hope you enjoyed the video. The whole idea of sharing with you today morning experience is that what we are trying to see sometimes may not be so visible. So the mist, when it clears away, just as in the first half of the video, we have understood all the concepts. So when this mist clears away, we actually see the real thing. And that is really exciting. So I hope you enjoyed watching the coyote. Now let's look into the summary of what we have learned with the help of an excellent example. We'll sketch the graph of p of x, which is equal to minus 2 times log to the base 2 of x minus 1 plus 3. Now at this stage, I'm going to take my time to summarize all the concepts and go a bit slow, right? So let us first list all the transformations which we should be considering to sketch the graph of the given function, right? So each and everything here is related to transformations, right? So let's see how they are related. That negative is what? It is reflection on vertical reflection on x-axis, correct? This is first part. How about this 2? 2 is vertical stretch. So it is vertical stretch by a factor of 2. Now negative and then 1. This 1 means what? Horizontal translation. By how much? Just 1 unit. Which direction? Horizontal translation. 1 unit. Right. Correct. And 3 is vertical translation. Three units up. So combining all this, we get our transformed function. Now let us also look into the key points, right? So let's make our key points now. So whenever we are saying key points, it is with respect to the base function, which is log to the base 2 of x, correct? Okay. So let me make a table here so that we can clearly list our points. Let me make a horizontal kind of a table this time, since we have less space. Okay. So let's say we'll write down log to the base 2 of x, and then we'll write this function, which is minus 2 log to the base 2 of x minus 1 plus 3. Okay. So if we have a point in general, which is xy, how is that going to get transformed? As far as the x value is concerned, we are only adding 1 to it, so it becomes x plus 1, correct? As far as the y value is concerned, we are multiplying by minus 2 and then adding 3. So we get minus 2 times the y value plus 3. So that is the basic transformation. Do you see the transformation formula here? That is how we are going to transform. So now let's look into the features. Okay, now one of the key features is the end behavior. So when I say x is approaching for logarithmic function 0 from the positive side, y basically approaches negative infinity. Now as far as the x value is concerned, we have to add 1. Do you see that addition of 1, how it plays a role? So now we are saying when x approaches 1 from positive side, y approaches what? Negative of this value, right? So negative 2 times. That means positive infinity, right? So this time positive infinity. Do you see that major change? It's a huge change now, right? So let me just sketch this for you, and then we'll try to understand what is really happening, correct? So earlier we had a logarithmic function which was shown like this. So this is your log to the base 2 of x, perfect, the original function, on which we had been considering 3 points, right? Let these be the 3 points. And that was our end behavior. Is that clear to you? 5 key points. Now we are focusing on this point. See what is happening. When I say minus, this point actually shoots up. That is minus, right? So that minus makes it shooting it up, but then you are moving it by 1 unit to the right. That means the vertical asymptote has shifted from the y-axis to a position which is 1 unit to the right, which is practically here. Do you see that? So it moves here. So this is the value which is now equal to x equals to 1. So your graph is on the right side of this red line, and that is your vertical asymptote. Does it make sense to you? So this 1 actually shifts all these points by 1 unit to this side. Does it make sense to you? Okay. Now, so combination of these two, as far as the value infinity goes, means that you are now approaching here. Does it make sense to you? That is the first criteria. Now let's look into the points as such. So this point here was at half, the value was -1. Now to half, I'm going to add 1 plus 1. That means 3 by 2, right? 3 by 2 is 1 plus half. The y value gets multiplied by -2, so that this becomes +2 plus 3 makes it 5. Does it make sense to you? So this particular point moves from here to, let me break the scale here since, they are going to be bigger numbers. So 1.5, that is, right? This was 2 for us. So somewhere here, it has shot up to a very high value, right? So let's say this point here is now 1.5 or 3 over 2, 5. Does it make sense to you? Right? So that's your point number 2. Perfect. Now, let's look into the third point here, which is, so we have considered these are the relations, right? Now we'll see the next point here. The next point for us is this point, right? Now we are focusing on this, which is add 1, the value is 0. So if I multiply, 1, we have to add 1. So let's make it 2. And if I multiply anything to 0, it remains 0. However, we are translating 3 units up. So it changes to 3 units up. Does it make sense to you? So this particular point now moves from 1, 0 to 2, 3, right? So now it is at 2, earlier this point. So somewhere here, right? So 2, 3. So here we have a point which is 2, 3. Perfect. That's your next point. Now, the third point, which is a key value for us, is at 2, the value was 1 in the original function. So 2, I'm going to add 1 to it, it becomes 3. To 1, I'll multiply by -2, it becomes -2, plus 3 will give me +1, correct? So the third point moves to a position which is 3 units away, but 1 up, right? So 1 up. So you see how we are getting this graph, correct? So this graph here is kind of like this. Does it make sense? So that is the graph of our function p of x. Does it make sense to you? So you can see that when x is approaching infinity, y was earlier approaching positive infinity, but now when x is approaching infinity, y approaches negative infinity. So that becomes the end behavior. Perfect. So that is how we'll get the graph of our transformed function now. Does it make sense? So the major change here is that the domain has changed. The domain of this function now is what? Domain is x belongs to real numbers where x is greater than 1. Well, range is all real numbers, right? Y belongs to real numbers. That's okay, but the domain has changed. Even the end behavior has changed. Instead of approaching negative infinity on the vertical asymptote, it approaches positive infinity. But when x approaches infinity, it approaches negative infinity. Right? So that is how we get our transformations done. So I hope that helps you to understand the complete concept of sketching logarithmic functions. Right? Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. So we began with understanding of logarithmic functions. We first sketched it with the help of reflecting exponential function on y equals to x, and then did all the transformation after applying the rules. So what you also learned here is rules of logs, right? And I hope you also like the video in between. That is, with the clarity of vision, we can see much more than what is near us. Sometimes the danger, the death is by our side. So with clear vision, we can be very conscious. I hope that helps. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.